Okay, welcome back, students. Let's continue on. Let's finish up chapter 6 here with section 6.4. Okay, 6.4 is on properties of linear transformations. Okay, let's look at composition of linear transformations. Okay, definition. Okay, let T1, transformation 1, go from U to V, capital U, sorry, capital U to V, and then T2 go from V to W. Okay, so we're mapping U to V, and then we're mapping V to W. Be two linear transformations. Okay. We define the composition or product, we call it the product, T1, T2, mapping U to W, jumping through V. Okay, so that's a, oops, that's a U. Okay, U to W by the transformation T2, T1 of U. Okay. Okay, taking vector U through T1 and then through T2. Okay, equals, okay, T2 of T1 of U. So we do T1 first, and then we have T2 on top of that. For all U, in U, okay, in vector space U. Okay, theorem. Okay, let T1 go from U to V. U to V, and T2 go from V to W. Okay, be two linear transformations. Okay, then okay, and then T1, T2, T1 going from U to W is also a linear transformation. Okay, those have the same properties. Okay, example 1. Let T1 be Mn of R mapping to Mn of R. Okay, so we've got one square matrix mapping to another square matrix. Okay, and T2 mapping Mn of R to just R. Okay, be a linear transformation such that T1 of A, the transformation of A is equal to A plus A transpose. Okay, so it's going to take all my matrix A's and then it's just going to add it to its own transpose. Okay, and T2 of A is equal to the trace of A. Okay, I haven't talked much about trace in a while. The trace of A. Okay, which is just the summation of the diagonal. Okay, so find T2, T1 of A if A equals 2, -1, -3, and 6. Okay, so what does this mean? This means that we're going to do T2 of T1 of A. Okay, so we're going to do first T1 of A. We're going to take A and add to it its own transpose. Okay, so what is A transpose? Well, A transpose is equal to, we just swap the rows with columns. It becomes 2, -1, -3, 6. And I want to add that to those together. Okay, and so we're going to say that this is going to be T2 of 2, -1, -3, 6 plus 2, -3, -1, 6. Okay, so this is equal to T2, the transformation of 2 plus 2 is 4, -4, -4, and 12. So we'll transform that. Well, the transformation of this new matrix, okay, I want the trace of that. Well, it's no longer A that we're finding the trace of. We're finding the trace of this T1 of A, okay, but you know the rule still holds. We just want the trace of this new matrix, and so this is going to be 4 plus 12. So it's T2. It's the trace of this new matrix. Okay. It's the trace of 4, -4, -4, and 12, which is equal to 4 plus 12, which is 16. So it does take me to a real number. Okay. Okay, definition. A linear transformation T going from V to W is said to be one to one if, so 1 to 1, if distinct, oops, okay, if distinct or different elements in V are mapped via T some transform, okay, some elements in V are mapped via T, okay, to distinct elements in W. Okay, that is, wherever V1 is not equal to V2, okay, whenever we have two distinct vectors, okay, we have T of V1 not equal to T of V2. Okay, so if the inputs are unique, then the outputs have to be unique. That's 1 to 1. Okay. No repeated inputs and no repeated outputs. It is said to be onto if the range of T if the range of T is the whole of W, okay, that is every vector W in W is in the image under T. Let's get rid of the under of at least one vector of V in V, okay, which is the preimage. V is the preimage. I haven't talked much about image or preimage. Okay, but the preimage is where you start, the image is where you end up. And what we're saying is we're saying that basically it's onto if the image is complete. Okay, we don't have anything mapping to something outside of W. So to have onto, you can have repeated domains. To have 1 to 1, you cannot have repeated domains or repeated ranges. Okay, but to go onto just means that the range is closed. Okay, so basically 1 to 1 is this is the preimage and this is the image, and everything in the preimage has a 1 to 1 correspondence to the image. Okay, where the transformation takes you from the preimage to the image. What we're talking here is V to W. Okay, that's 1 to 1. Okay, onto means that no matter what I have in the pre-image, okay, I only end up with stuff that's in the image. Okay, I'll have just 4 dots here. Okay, so no matter where we come from the pre-image, we only end up in the range that is the image. Okay, so we only end up in W. We don't, W is basically complete. Okay, so and this is onto. Now, if you have one-to-one and onto, it means that basically your domain and range are closed. Okay, and that's kind of the nicest situation to have. Okay, we like things that are one-to-one and onto. Okay, it means we can find inverses and we go back and forth, and it's nice and easy. A theorem. Okay, let T go from V to W be a linear transformation okay, then T is one-to-one if and only if the kernel of T is equal to the 0 vector. Okay. It just means that all vectors that could produce a 0 go to the 0 vector. Okay, so the null space is equal to 0. Okay, then it's one. Then it's one-to-one. Okay, proof. This is the first proof we've done in this class. Just because there's so much material to get through. It's so hard to spend any time on proofs. But let's do a proof. Okay, very quick proof. One-to-one dictates that T of 0 has to go to 0. Okay, and this is the, I'll do 0 vector, and this is the only mapping to 0. Okay, 0 has to map to itself. Okay, otherwise it's not one-to-one. If 0 mapped to other things, okay, we had a repeated domain, then it wouldn't be one-to-one. And if the range of 0 mapped back to multiple items, that also would not be one-to-one. Okay, so either your domain maps to one unique 0, or and your range maps back to one unique 0. Otherwise, you don't have one-to-one. So therefore, the kernel of T, which is the null space, has to have one value in the beginning and one value at the end. And that just happens to be the 0 vector. And this is the only mapping to 0. Therefore, the kernel of T is equal to, oh, you know what? I'm getting my symbols wrong here. This should just be parentheses. The kernel of T is equal to the null space that contains just the 0 vector. Okay, so and the dimension of that is 0. Okay. Okay. A linear transformation T, V goes to W, is 1, 1 to 1, if and only if the kernel of T is equal to the 0 vector. Okay. And 2, onto, if and only if the range of T is equal to W. Okay. Okay, number 2. Let T go from P2R to P2R. Oh, my numbers are off. P2R. Okay, be the linear transformation okay, T of AX plus BX plus CX squared. Okay, so my standard quadratic is going to get mapped to 2A minus B plus C plus B minus 2A X plus CX squared. Determine if T is 1 to 1. Whoops, 1 to 1. Onto or neither. Okay. Could be both too, but okay. Is it 1 to 1? Is it onto or neither? Or both? Okay, if P of X is equal to okay, A plus BX plus CX squared. Okay. And then the kernel of T is equal to all values of P in P2R, okay, such that the transformation of P equals 0. Okay. Okay, so in order for the kernel of T, let's look at what the kernel of T would have to be here. So the transformation of any value of P would have to equal 0. So we'll just say that 2A minus B plus C plus B minus 2A, okay, X plus C of X has to equal 0. I'll write it like this, plus 0x plus 0x squared. Right? The constants would have to be 0. The linear coefficient would have to be 0, and the quadratic coefficient would have to be 0. Okay. Okay, and so we could say that 2a minus b plus c would have to be 0. B minus 2a would have to be 0. And c would have to be 0. Okay. Okay, so we know what c is. C is 0. So we can lock that in. Okay. However, if we plug in 0 here, we get 2a minus b is equal to 0, and that tells me that b is equal to 2a. Over here, I get the same thing. I get b is equal to 2a. So I don't necessarily have to have b be 0 and a be 0. I can, but there are other things inside my kernel. Unfortunately, there's a whole line. There's a whole line, a whole line of two-dimensional points that for B and A are, that represent would give me 0, all these zeros. So we say that the kernel of T is equal to all the values a plus bx plus cx squared, such that b equals 2a and c equals 0. Okay. Okay, and so this is equal to all the values of a plus bx. Okay, but what is b? B is 2a. So let's plug in a 2a here. 2ax plus what is c? C is 0. 0x squared. Okay. So now all we have is a. We have everything in terms of a and x. So that's one if x is an element of the real numbers. So that I can rewrite as the kernel of that. This thing I could factor out an a from, and that would give me 1 plus 2x. Okay, so my kernel is a times 1 plus 2x, where a is an element of the real numbers. Okay. And this thing is not equal to 0. Okay, there's a whole bunch of values that will work there. And since the kernel is not 0, it is definitely not 1-to-1. Okay, so T is not 1-to-1. Okay, so let's look at the at onto. Is this thing onto? So from the general rank nullity theorem, okay, we know that the dimensions of the kernel of T, okay, plus the dimensions of the range of T has to equal the dimensions of V. Okay. Okay, so the dimensions of the kernel of T. Well, what is the kernel of T? The dimensions of the kernel of T. The kernel of T we saw was a plus or a times 1 plus 2x. Okay, so it Okay. Okay. Plus the dimensions of the range of T. Okay, is equal to the dimension of P, P 3, right? P2 of R, right? That was what we started with way back here. Yeah, P2R. Okay. Okay, so the dimensions of A of 1 plus 2x. Okay. And that dimension is 1. It's got dimension 1. Okay. So let's just verify that. Okay. Okay, so that's the number of vectors. The dimension is the number of vectors in any basis of the kernel of T. Okay. Yeah, and so how many vectors do we have here? We only have the one vector. Okay, we only have the one component. Okay, even though it's two-dimensional, 1 plus 2x, we only have that one vector. Like if we go back to the transformation, we have, you know, we have 1, 2, 3 vectors. Here we only have that one vector, so that's a one-dimensional. Okay, that's one-dimensional. Okay, plus the dimensions of the range of T equals the dimensions of this. Well, the dimension of P2R is 3. There's always n plus 1. So if we subtract 1, okay, we get the dimension of the range of T, okay, to be equal to 2. Okay. And that is not 3, which is not equal to 3. Because, and why that's important is because the range of T is 2. The dimension of the range of T is 2. However, the dimension of what we're mapping to, which is W, right? Okay. Which is not the dimension of W, which is equal to 3. Okay, the dimension of W is, again, we're mapping to P2R, right? The dimension of P2R, again, W is P2R. Okay. And so that dimension is 3. Okay, and so since this is less than, since the range of T, the output of T has less dimensions than what we're going on to, okay, what we're mapping onto, this is not onto, okay, because it won't fill the whole vector space, the whole destination vector space. Okay, therefore, the range of t does not equal w, and t is not onto. Okay. So neither. So they were neither. They were neither 1-to-1 nor onto. Okay, corollary. Let t go from v to w. Excuse me. Okay, be a linear transformation where v and w are finite dimensional. Okay, then if t is 1-to-1, then the dimensions of v is less than or equal to the dimension of v is less than or equal to the dimension of w. Okay. 2, if t is onto, then the dimension of v is greater than or equal to the dimension of w. And 3, if t is both 1-to-1 and onto, then the dimension of v has to equal the dimension of w. Okay. Okay, if the dimension v, if the dimension of v is equal to the dimension of w, then t is 1-to-1 if and only if it is onto. Okay, so they have to be both. Okay. Okay, definition. Let t, let t go from v to w, a linear transformation if t is both 1-to-1 and onto, then t, oops, capital T has an inverse transform. Okay, such that transform, would be going backwards from W to V. Okay, an inverse transform, what we call T to the -1 power, okay, or T inverse, such that T of W, or sorry, T inverse of W would equal V. Okay, so T inverse W would equal V. Okay. But it has to be one-to-one on onto, but we're going to have a vector in W go to a vector in V. And there's going to be a one-to-one pairing of all these vectors. Okay, it just means that, look, I can go forwards and backwards if it's one-to-one and onto. Okay, theorem. Let T go from Rn to Rn be a linear transformation with matrix A. Then T inverse exists if and only if the determinant of A is not equal to 0. And the matrix of T inverse T inverse is A inverse. Okay, so the inverse matrix would give me the inverse transformation. Okay, definition. Let V and W be vector spaces if there exists a linear transformation T that maps V to W that is both one-to-one and onto we call T an isomorphism and we say V and W are isomorphic. Written V is congruent to W. Okay, but we wouldn't say congruent, we would say isomorphic. Okay, V is isomorphic to W. But we use that little congruency symbol to represent isomorphism. Note. If the dimensions of V are not equal to the dimensions of W, V and W are not isomorphic. V and W are not isomorphic. If the dimensions of V equal the dimensions of W, then V and W might be isomorphic, but they don't have to be. Might be isomorphic. Okay, number 3. Okay, A, determine oops, determine an isomorphism P going from R3 to P2R. Okay, do they have the same dimensions? Yeah, R3 has 3 dimensions and P2R has 3 dimensions. Okay, so can they be isomorphic? Sure. Are they? I don't know yet. Okay, what was the definition of isomorphism? It's so that they're both 1-to-1 and onto. Okay, so what would be an R3? Well, R3 would be some 3-dimensional vector. So we could call that 3-dimensional vector, okay, in R3, we could call it ABC if we really wanted to. A, B, C, right? That's the 3-dimensional, that's a general 3-dimensional vector that we would use, okay? And so A is going to get mapped to a distinct character in P2R. B is going to get mapped to a distinct character in P2R, and C is going to get mapped to a distinct character in P2R. So we would say that T of ABC, or the transformation that involves ABC, okay, would equal A plus BX plus CX squared. And so all of the unique three component vectors that I could come up with would create unique quadratics. Okay, and so there is this is 1-to-1, this is onto. Okay, and so this is an isomorphism. Okay, B, determine an isomorphism. Oops. Isomorphism. Okay, of T going from R4 to M2R. Okay, so again, we could say that the transformation from A, B, C, D this time, okay, would then go to a 2-by-2 matrix that has 4 components, A, B, C, D. Okay, and they do have the same dimensions. They each have a dimension of 4. And they're each at every unique component in T has a corresponding unique component in, or sorry, not in T, in R4, every unique component in R4 has a corresponding unique component in M2R, and therefore they are 1-to-1 and onto. Okay, what if we did this? What if we said that we wanted to determine an isomorphism where T where T gets mapped from P3R to M2R. What would we do there? T gets mapped from P3R to M2R. Well, P3R has 4 dimensions and is dimension 4, and M2R is dimension 4, so this should work. So this would be the transformation from a plus bx plus cx squared plus dx cubed, okay, goes to a, b, c, d. Okay, so those are some isomorphisms. Okay, theorem. Okay, let A be, okay, be an n by n matrix with real elements. Okay, and let T go from Rn to Rn, okay, be the matrix transformed okay, by T of x equaling ax. Okay. Okay. Then the following okay, then the following are logically equivalent. Okay, the following logically equivalent. One, A must be invertible. Two, T is 1-to-1. Three, T is onto. Four, T is an isomorphism. Okay, and five, T inverse exists if the determinant of A is not equal to 0. Okay. So as long as the determinant is not equal to 0, we're good. Okay, example 4. If T goes from R2 to R2, has matrix A okay, then 1 is A onto. Or sorry, is A 1-to-1. Sorry, I should say A 1-to-1 first. Let's do 1-to-1. 2-1. Okay. We have this transformation matrix. Okay, is at 1-to-1. Okay, well, let's look at the kernel. Okay, let's look at the kernel. So, right, because what we're saying is T of x is equal to A of x. Right, so we're going to multiply this matrix times something, and then we're going to get zeros. Well, what's the only thing that's going to get us zeros? Right, if we take 1, 2, 3, 4, and we multiply by x1, x2, and we want that to be zeros, right? What's the only thing that's going to get us zeros there? Well, it's zeros. it's x1 equals 0 and x2 equals 0. I can show that by creating an augmented matrix, 1, 2, 3, 4, and then REFing this. This just goes to 1, 0, 0, 1, 0, 0. Okay, and so that tells me that x1 had to be 0 and x2 had to be 0. So the 0 matrix is the only thing that gets me the 0 matrix. And so since the kernel of T, since the kernel of T is equal to the 0 matrix, and that's the only thing that gets me the 0, okay, it is 1 to 1. Okay, therefore, T is 1 to 1. Okay. Okay, what about onto? Okay. 2 is A onto. I guess I should say therefore A is 1 to 1. Okay. Okay, is A onto? Yeah, A is onto if the range, okay, has the same dimensions as where we're going. Where are we going to? We're going to R2, right? So as long as the range has the same dimension as R2, we should be good. Okay, so what's the range of T? Okay, the range of T is equal to the column space of A, right? And so what's the column space of A? Well, if we look at our leading ones here, we've got, okay, that, and so our column space of A is 1, 3, 2, 4. It's the span of 1, 3, and 2, 4. Okay, which is 2 vectors. Right? That's two vectors right there. And so what's the dimension of the range of T? The dimension of the range of T is equal to 2, which is the same as the dimensions of the R2, which is what we were going to, is equal to 2. So yeah, we can get onto. Okay, we're going to fill up. We're going to fill up, okay, where we're going to. If we call that, you know, V and W, if we call this from V to W, we're going to fill up W. Okay, it's going to have the same dimensional space as the range, as the output. And so, okay, it is onto. Okay, so since it's 1 to 1 and since it's onto, okay, we know that an inverse exists. An inverse, not only an inverse, if we look at our theorem here, not only does this inverse exist, the inverse transformation exist, but it is attained, okay, it is attained by getting the inverse of A, okay, which was back here somewhere. There's a theorem right here that says let T go from Rn to Rn be a linear transformation of the matrix A, then T inverse exists if and only if determinant of A is not equal to 0, and the matrix of T inverse is A inverse. So if we can find out what A inverse is, okay, then we know what T inverse is. Okay, so let's find what T inverse is. Find the inverse of t. Okay, so find t inverse, okay, which is attained from, they're not identical, but it's attained from A inverse. Okay, find t inverse. Okay, so let's first let's look at matrix A. A was 1, 2, 3, 4. Okay. Okay, so let's look at the determinant of this first. Okay, what's the determinant of A? Well, it's just 1 times 4 minus 3 times 2, which is -2, which is not equal to 0. Okay. Okay, the next thing we can do is find the inverse of this. We can use our calculator. We could do an augmented matrix. It really doesn't matter. Okay, and inverse is going to be the augmented matrix 1, 2, 3, 4, 0, 1, 0. Okay, 1, 1, 0, 0, 1. Okay, we want to turn that into, okay, if we were to REF this, actually REF that, okay, we would end up turning this into 1, 0, 0, 1, and we would get -2, 1, 3 halves, and -1 half. And so this would be my A inverse. Okay, so A inverse is equal to -2, 1, 3 halves, and -1 half. Okay. And then let's find T inverse. What would be the T inverse? Okay, so, well, the T inverse of X would be equal to A inverse times X. Okay, the T inverse of X is equal to A inverse times X. Okay, so this is going to be equal to -2, 1, 3 halves, -1 half times X1, X2. Okay, and if I were to multiply that out, I would end up with -2x1 plus x2, okay, over 3 halves x1 minus 1 half x2. And so I could rewrite this as T inverse of x1, x2 is equal to two components, -2x1 plus x2 and 3 halves x1 minus 1 half x2. Okay, that would be the inverse. Okay, so, okay, compare that to t, right? What would be the t of x1, x2? The t of x1, x2 would basically map it to x1, 1x1 plus 2x2, and then it would map it to 3x1 plus 4x2. Okay, and so what we're doing is we're saying, look, if we plug in x1, x2, and we're going to get an output, okay, if our domain was x1, x2, we would get an output that would be x1 plus 2x2, and then 3x1 plus 4x2. That would be our output. And then what would we do with that output? We would plug it into our inverse. Okay, I would feed this back in here, and I would feed this back in here, and I should come out with my original value. Okay, as long as I plug in that value into x1 and that value into x2, I should undo what was done. Okay, and if you want to try it with a value, you can, just see like, oh, does it work? Well, let x1, x2 be whatever you want. Okay, you could let it be, we could let x1, x2 be, I don't know, 5, 6. If you did t of 5, 6, what are you going to get? You're going to get 5 plus 12, so that's 17. Okay, and then you're going to get 15 plus 24, right? Sorry, 15 plus, 24, which is 39, right? Okay, and then if we inverted that, T inverse of 1739, okay, we plug that in, what would I get? I would get -2, okay, times 17, right, -2 times 17 plus 39, and then I would get 3/2 times 17 minus 1/2 times 39. Okay, so what are we going to get out here? Well, this is going to be -34 plus 39. That's the easy one. That's 5. Okay, and then over here we're going to get 51 minus 31 divided by 2, or minus 39 divided by 2. That's 12. 51 minus 39 is 12. 12 divided by 2 is 6. So I do get 5, 6 out, back out. Okay, so they are inverse transformations. Okay, and that's chapter 6. So I will see you in the next chapter.